Then we want to continue on our themes from yesterday, where we're kind of putting things together, what we know about derivatives and what we know about definite integrals. Admittedly, we've just started talking about definite integrals. We're thinking of definite integrals as area under a curve. We're putting that together with the stuff that we know about the derivative. When the derivative is negative, the function is decreasing, and the area will tell you by how much. When the derivative is positive, then the function is increasing, and the area tells you by how much. We're thinking of definite integral. We first think of definite integral as area under a curve and above an interval. But when we looked at the fundamental theorem of calculus, we're thinking of the definite integral as total change in the function. When we find the definite integral of a rate of change, we get the total change. When we integrate a rate of change of a function, we get the amount of change in the function. Our primary example of this is that velocity or speed, if we just want to keep everything going one direction, speed is the rate of change of position with respect to time. It's change in position divided by change in time. If we integrate the speed over an interval of time, it will give us the distance traveled in that time. This is the other direction of the question. If we look at the graph of the position, the slope will tell us the velocity at any given moment. Then we got into a bunch of technical stuff, finding derivatives, product rule, quotient rule, chain rule, and all of our rules, and a little bit of finding antiderivatives. We've got one rule right now for finding antiderivatives. We can find the antiderivative of a power function, and that's it. That's all we need. We can get a lot of mileage out of that. All right, let's take a look at a graph, this graph and the setup. The setup is, let capital F of x be the definite integral from 2 to x of f of t dt, and here is a graph of f of t. We're playing the same game that we played yesterday with the graph, only I kind of opened up a little bit different. Notice that what we did was we're defining a function capital F as the definite integral from 2 to x of f of t dt. Here I am using the second part of the fundamental theorem of calculus to define an antiderivative. So this is what it looks like when we use the second part of the fundamental theorem of calculus to construct an antiderivative. So here, here we are constructing an antiderivative using a definite integral, just like the fundamental theorem of calculus says that we can. I didn't specifically state that I'm constructing an antiderivative. I'm just constructing the function with the definite integral. The expectation is that you recognize this as constructing an antiderivative using the definite integral. So what that means is that the capital F function that I'm constructing, words hard today, the capital F function is the antiderivative of the graph, of the function shown in the graph. So what I mean is we're looking at capital F prime. So if capital F is an antiderivative of little f, then the derivative of capital F is f. So these are the things that we want to notice about the setup in this problem. I said capital F is the capital F is the definite integral from 2 to x of f of t dt. That should make you think this looks like we're setting up with the fundamental theorem of calculus. That should make you think about the second part of the fundamental theorem of calculus and recognize that we are constructing an antiderivative using a definite integral. The second fundamental theorem of calculus says that a function constructed this way, capital F, is an antiderivative of little f. What that means is capital F prime is equal to little f. What that means is that this is my way of saying, here is the graph of the derivative. Yesterday, I played the game differently. I just drew a graph and said, this is the graph of a derivative. But here, I'm telling you that in a different way. I'm telling you that by making you recognize the second fundamental theorem of calculus. So I wouldn't say all this part in red. That's the part that you're thinking about. That's the part that you recognize. How's everybody okay? All right. So we're looking at the graph of the derivative. Let's go through and figure out what we know based on looking at the graph of the derivative. Let's practice reading what's going on in the graph of the derivative. So when we're looking at the graph of the derivative, so this is the graph of f of x. So we know that this is the graph, secretly, we know that this is the graph of f prime. So let's write down the stuff that we know. The sign of the derivative tells us the direction of the function. The sign of f prime tells us the direction of the function. So f prime is positive from 0 to 1 and from 3 to 5. So we might notice that f prime is positive on the interval from 0 to 1 and from 3 to 5. That was a really lousy way to read union. I want the union of these two sets, and union should be like 4. That's the word I should use for union. But no one called me on it, so minus 10 points for everybody. I'm just kidding. It's minus 1,000 points for everybody. I'm just kidding. 0 points for everybody, 10 points for me. So what this tells us is that from 0 to 1 and from 3 to 5, our function capital F should be increasing. But we know more now. We know more stuff now. We know that when the derivative is positive, the function is increasing, and we also know that the area will tell us how much. And we can easily see how much area we have. From 0 to 1, we see an area of positive 1. So our function, capital F, will increase by 1 on the interval from 0 to 1. And then from 3 to 4 and from 4 to 5, let's break it up into a triangle. There's going to be another 1 on 3 to 4 and 2 from 4 to 5. We've added to what we know before. We know that the function is increasing where the derivative is positive. The area will tell us how much increase we get. We also notice that f prime is negative on the interval from 1 to 3. So that f is decreasing on the interval from 1 to 3. But we know more now. We know that the area tells us by how much the function will decrease on those intervals. So from 1 to 2, I'm going to break it up just like we did yesterday. From 1 to 2, we'll decrease by 1. And from 2 to 3, we'll decrease by 1 again. So we'll decrease by -1 on the interval from 1 to 2, and by -1 again on the interval from 2 to 3. I don't really have to exclude the 1 and the 3 when I'm saying about how much they decrease. So now we can see what's going on. Whatever we start off at 0, we go up 1, then down 1, then down 1 again, then up 1, then up 2. That's just what we read by the areas. We knew we were going to go up, down, and then up again based on the sign of the derivative. We knew we were going to go up 1, down 1, down 1, up 1, up 2 by the area. But we know more than this because we're looking at the derivative and we can see what direction the derivative is going. So we can see that f prime is decreasing on the interval from 0 to 2. So our function is going to be concave down on the interval from 0 to 2. So now we can see not just the function going down, but we can see the function concave down and decreasing. Concave down and increasing, then concave down and decreasing. And then from 2 to 4, the derivative is increasing, so the function will be concave up. So our function will be concave up on the interval from 2 to 4. Then on the interval from 4 to 5, the only part that we haven't looked at the concavity, we see that the derivative is flat on the interval from 4 to 5. So the function is not going to have any concavity on 4 to 5. We say no concavity by saying linear. So linear is another way to say no concavity, neither concave up nor concave down. We also see some other things. We know that our function, it goes from increasing to decreasing at 1. So f prime of 1 is equal to 0. And f prime is changing from positive to negative. So we see that we're going to have a local maximum at 1 and a local minimum at 3. Because the derivative is changing sign, so the function is changing direction. So we see that f has a local max spelled X wrong. How does a dude that was a teenager in the 90s, no, early 20-something, in the 90s, collecting comics, spell the letter X wrong? I know none of you were around in the 90s, but it was fucking X everything. Everything was X. X, 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 X. X-Force. They didn't make that dumb stuff up just for the movie. That was a real thing. It was an X-Force. They had one called executioner's tail, or at least it was supposed to be executioner's tail, but they spelled it executioner's tail. So in all the comics, it just said executioner. I'm like, oh, what's a what the? It was just misspelling everything. And Mountain Dew was the extreme drink of choice. I know it's like a video game drink now, but back in the 90s, apparently was like a sports drink. And you were supposed to drink it out of the bottle by holding it above your face and letting it pour into your mouth. Because it was Mountain Dew, extreme soda. I don't know. I spelled X wrong. F has a local max at 1 because we're changing from, the derivative changes from positive to negative. So the function changes from increasing to decreasing. And we'll see that F has a local minimum at 3. Because the reverse happens. The derivative changes from negative to positive, so the function changes from decreasing to increasing. So let's make a table of values. Let's mark the changes, first of all, in our table of values so that we can draw a picture of F. 0. So the first thing that happens is from 0 to 1, we will see an increase of 1. From 1 to 2, we'll see a decrease of 1. From 2 to 3, we'll see a decrease of 1 again. From 3 to 4, we'll see an increase of 1. And from 4 to 5, we'll see an increase of 2. We need a place to start. Yesterday, I had to tell you where the graph should start. I had to tell you that f of 3 was equal to 0. I just made that up. I had to tell you something. I had to tell you somewhere in the vertical, which vertical shift we are talking about. All the antiderivatives will have the same shape. They'll all just be vertical translations of each other. In this problem, I did tell you where to start. I did give you a value of this function. And that happened when I defined the antiderivative. I said capital F is the definite integral from 2 to x of f of t dt. So what value do we have in this table? What do we know? What can we fill in right away? I didn't specifically say that f of something is equal to some value. I've made you figure that out. Without knowing anything about little f, then I can evaluate this function for one particular value of x. And what is that value of x? So one thing we want to note, by the way that I've defined the function, I have secretly given you a value for the function already. What value of x can we plug in where we can evaluate it without knowing anything else? And what will it equal? One of those math top line. Type your answer in the chat. Oh, that's not right. That's not right. Yeah, you got it. Yeah, and it's like just tell us the answer. Isn't that what we're here for? So I know some of you are already. I have to do it. You don't have a chat, so I have to do it by reading your minds. And I know some of you were thinking it already. So I want some more contrast. I'm going to use red because this is what we were supposed to. Red is the thinking color. So we can evaluate this function at one value without knowing anything else. We can evaluate this function at 2. Because if I want to find f of 2, I do the definite integral from 2 to 2. So I'm asking if f of t is the rate of change, how much will the function change when x goes from 2 to 2? How much will the function change? If by your silence you mean 0, that is correct. So good job. Everybody was correct. So by defining the function this way, when I say capital F of x is the integral from 2 to x of f of t dt, I am telling you that f of 2 is equal to 0. Remember, the definite integral from a to b of f of x dx is capital F at b minus capital F at a. So if we do the definite integral from a to a, I want to do capital F at a minus capital F at a. And I don't care what's happening with the function. Those two things are the same. So capital F at a minus capital F at a is 0. So we are given that f of 2 is equal to 0. And once we have one value, since we know all the changes, we can fill in the rest. It's like a boring version of the Nashville numbering system. It's 1, 4, 5, and then I just got to tell you what key we're going to play in. So we know all the changes. We know that f of 2, capital F of 2 is equal to 0 because the integral from 2 to 2 is 0. And we know the changes. 0 plus 1 is 1, minus 1 is 0, minus 1 is negative 1, plus 1 is 0, plus 2 is 2. And we can see our local minimum at 3, when x is 3, and our local maximum when x is 1. Now this is just the values. We can plug these in, plot these on a graph and get the shape. So we're gonna go up, then down, then up again. But we know more than that. We can actually put in the concavity of the graph. So I'm gonna start off at 0. We'll go up 1, then down 1, then down 1 again, then up 1, then up 2. We're going to draw concave down from 0 to 2. We'll change concavity at 2, and so we'll have an inflection point because we're changing concavity. And then we'll be concave up from 2 to 4, and then from 4 to 5, we'll have no concavity. So I'll just draw a line. We can read a lot from the derivative. The sign of the derivative tells us the direction of the function. The area tells us how much. The direction of the derivative tells us the concavity of the function. Any questions? The same kind of thinking can go further. We can do third derivatives and fourth derivatives and stuff like that, but we really just kind of need to stop at two. Because inflection point is kind of like the last interesting one that we have. After that, it's getting kind of moody. But we should know what we need when we talk about an inflection point. An inflection point is a change in concavity. So a function might be still increasing, but if we've crossed an inflection point, the rate of increase is slowing down. That's what we mean when we say we've reached an inflection point. I think about this because we just went through the pandemic and everybody's graphing all the infections. The number of infections will always be increasing because you either have it or you don't. I guess if you got a false positive, go, oh, subtract one. I just sneezed. That was it. That was false alarm, everybody. But if we look at the number of cases, that has to be increasing, right? The number of cases that we've had is going to be increasing. So is it increasing, and is the rate of increase increasing? Is our second derivative positive? Are we concave up? Or have we reached an inflection point and the rate of infection is slowing down? So still increasing, but at a lower rate. That's what we're talking about when we think about an inflection. So the inflection point that we find here is that our derivative, our slope is decreasing. Our slope is decreasing, and then after the inflection point, the slope starts increasing again. The function is decreasing through the inflection points, but the rate of decrease has stopped, and the rate of change is now increasing, and that's represented with the concave up. How's everybody okay? Everybody looks so stoked. I'm assuming. It's what it looks like when your team is winning. You stand up. Maybe what I need more sports. I need like put a scoreboard up. Scoreboard telling the fans when to cheer. Maybe I need some walk-up music. Maybe that's the thing. This is why I couldn't be allowed to play Major League Baseball, because they let the players pick their walk-up music. And I would be changing it all the time. It's a very inappropriate thing. I would be up next in the batting order, but I wouldn't be on the field yet. And then they'd be playing the Afro Man song. I was gonna go back, but then I got high. And then there'd be like a whoop, and then I would go running out on the field. Like, sorry guys, sorry I'm late. Now, I don't know if you've ever been to a Italian wedding. I played a chicken dance when I was walking up there one time. That'd be great. That is the sole disqualifying factor that keeps me out of the major league. It's not that I can't hit, even though I can't hit or throw or catch. Not having good depth perception makes those things really difficult. But analyzing functions by looking at their derivative, if there was a major leagues for that, fucking A, I'd have my walk-up music. Any questions? Comments? Side remark. What we need to do now, our big plan now, is to practice some more of defining antiderivatives, and then go back and look at all kinds of situations where we can use our thinking about derivatives and our thinking about integrals. So second half of this class is going to be all kinds of applications and using the things that we know. Right now we've got like this general sense of things that we know. We know about how derivatives and antiderivatives are related. We know about this sign and this direction and this concavity business. So we want to apply all that to various situations. Any questions? And if you've read along in the book at all, you know that I'm going to be like distance, velocity, acceleration. That's going to be our first one. All right, that's gonna do it for today. I don't know what the other 10 minutes of example I had today was. It's just completely gone from my mind. That's because it's too hot. I think it melted. So that's gonna do it for today. I guess we're leaving early today. That's gonna do it for today. That's gonna do it for this week. I'll see y'all on Monday. Everybody have a good weekend and thanks for playing.